Isaac Newton viewed gravity as an invisible force acting across a vacuum, but Albert Einstein realized that bodies do not pull on each other directly. Instead, mass curves the geometry of space and time in its immediate vicinity. To navigate this geometry, we use a light cone. Imagine a flash of light in empty space. In 2 dimensions, the light spreads out in a growing circle. If we allow time to run up the screen, that circle traces out a cone. This cone defines the boundary of your future. It represents every region of spacetime you can ever hope to influence. When a massive object curves the fabric of the universe, it also curves these light cones. The closer you get to the mass, the more the cones tilt inward toward the center of the well. Understanding the universe requires charting these local coordinates. But the very first time physicists attempted to map the interior of a massive object, the math collapsed. In 1915, Karl Schwarzschild was calculating artillery trajectories for the German army on the Russian front. Between duties, he focused on a different challenge, finding an exact solution to Einstein's new equations for gravity. Schwarzschild simplified the problem by imagining a universe with nothing in it except a single point of mass. It was static, non-rotating, and perfectly symmetrical. His solution worked, but it revealed a point where the equation divides by 0. At a radius of 0, the density becomes infinite and the math breaks down. This is the singularity. He found a second problem spot at a specific distance from the center. At this event horizon, the curvature becomes so steep that escape velocity reaches the speed of light. Here, the light cones point straight up, trapped at the edge of the void. Einstein and his contemporaries initially dismissed these results. They assumed that such black holes were mathematical glitches that nature would never actually allow to form. By the late 1930s, that belief changed. Robert Oppenheimer showed that when massive stars exhaust their fuel, gravity pulls the material inward until the star collapses indefinitely. Black holes were no longer a theory, they were a physical reality. This created a conflict in the math. To an outside observer, an object falling toward a black hole appears to slow down and freeze at the horizon, never actually crossing it. This freezing effect is an artifact of the coordinate system Schwarzschild used. It is a mathematical distortion, much like a Mercator map of the Earth. While the map is useful for navigation, it distorts sizes near the poles, making Greenland appear as large as Africa. By substituting a different set of coordinates, the infinity at the event horizon disappears. The math now shows that an object can cross the boundary smoothly without noticing anything unusual. We can describe this as space itself flowing inward like a waterfall. Photons attempt to swim against the current, but at the event horizon, space flows inward as fast as light moves outward. Once an object passes this threshold, the flow of space exceeds the speed of light. Every possible future path leads inevitably down to the singularity. To see the full reach of these equations, we can use a Penrose diagram. This map compresses the infinite past, future, and distance of the universe into a single diamond shape, where light still travels at 45-degree angles. In our universe, we occupy the right side of the diamond. The diagonal line is the event horizon, and the horizontal line at the top is the singularity, representing the final moment in time for anything that enters. Schwarzschild's equations allow for a time-reversed version of this geometry. At the bottom of the map, we find a white hole, a region where matter and light are ejected outward, and nothing can ever enter. Completing the map reveals a mirrored universe on the left. This is a completely independent world, mathematically connected to ours by a wormhole at the center of the black hole. By extending Schwarzschild's geometry to its absolute limits, we find that a single stationary mass naturally describes a bridge between 2 separate universes. Real stars rotate, and since angular momentum is conserved, black holes must spin as well. This creates a Kerr black hole, which drags the surrounding space into a swirl called the ergosphere. In a spinning black hole, the singularity is no longer a point. Rotation stretches it into a hollow ring. Instead of crashing into the center, a traveler could theoretically fly straight through the middle of the singularity. This passage leads into an antiverse, a region where gravity repels instead of attracts. These theoretical maps describe what is mathematically possible, but the physical universe often prevents these geometries from forming in practice. The wormhole connecting our universe to another is unstable. As soon as it forms, the bridge pinches off and snaps shut faster than light can cross it. Attempting to reach the parallel universe inside a spinning black hole presents another obstacle. Because infinite time is compressed at the inner horizon, energy and light pile up there. This massive concentration of energy creates a secondary singularity. It seals off the ring, blocking access to any universes that might lie beyond it. Keeping such a bridge open would require exotic matter with negative energy, a substance that does not exist in any known physical system. Equations provide the coordinates for these theoretical landscapes, but the physical laws governing energy and matter dictate which regions of the map we can actually inhabit. The math shows us what could exist. Physics defines what does.